Good morning. I'm presenting this work on behalf of Richard Wood, who's provided these slides for me, so please excuse me if I am unclear about any of the details. The work I'm going to talk about is downscaling for the Northwest European shelf, focused almost entirely on the reanalysis rather than the forecast products, although I will mention the forecast in passing in a couple of places during the talk. So this is work that's done as part of the NowMaps partnership, which is providing both reanalysis and real-time forecasts to CMEMS for the Northwest Shelf MFC. So Richard Wood, as I say, provided these slides for me, but also a lot of work by John Tinker, Enda O'Day and Jenny Graham, particularly looking at developing some of the future capability for higher resolution modelling. I think much of what's in these first couple of slides has probably been covered both in sessions next door in the training room earlier in the week and ideas that have been touched on by previous speakers in the main sessions as well. But we know that global models are a fairly mature tool for large-scale ocean predictions, for analyses, reanalyses, but they're clearly limited in terms of the resolution in the regional shelf seas. So obviously there are exceptions increasingly nowadays, but typically global reanalyses are sort of 25 kilometre sort of scale. And we know that coastlines are at much finer scales than that, eddy frontal features, for example. So we need to have a higher resolution model to resolve those things. And kind of alongside that, obviously partly related, partly a distinct issue, is that global models generally, and again there will be exceptions, but they generally lack some of the key physical and biogeochemical processes that we're perhaps more interested in the shelf seas, so tidal mixing and benthic processes. And that can either be just because they haven't been viewed as a priority in global models, they're very expensive in global models, or the other aspects of the way that global models are formulated, whether that's the vertical levels or other aspects of the models, which mean that it's difficult to put those in. And increasingly those things are changing, as we've heard in various talks this week, but as a generalization, I think those two statements are true. And there's a few examples as I go through relating to those things. So this is the CMEMS Northwest Shelf prediction system. The model we often referred to as AMM, which stands for Atlantic Margin Model. It's a 7-kilometre model at the moment, so relatively low resolution, I guess, in terms of compared to some of the things we've just been hearing about. And operationally, it runs within the foam operational system. It's coupled to the URSEM biogeochemistry model. And so as well as producing the standard physical parameters for CMEMS, we also can produce details of nutrients, phytoplankton, zooplankton, and sediments. Because it's Shell Seas model, it's running on S levels, so it's got 50 S levels, including high vertical resolution at the surface, so around 1 metre at the surface. And at the moment, one thing to note is that this model, both in operational mode and in reanalysis mode, is only assimilating sea surface temperature. So there's no profile assimilation and no altimetry assimilation at the moment, although that's going to be changing next year. So I thought I'd mention a little bit about the differences between our reanalysis system, which provides the multi-year product for CMEMS, and the near real-time operational forecast system. So ideally, these two things would be pretty consistent, and in general they are. In terms of the science configuration of the model, that's exactly the same. But inevitably there are differences, and perhaps more differences than we would like at this stage, and we're hoping that some of these things will become more consistent, certainly next year and the year after that. So the reanalysis, like most reanalysis products, uses the era interim atmospheric forcings. It's using the core bolt formulae as within the NEMO model. We're using E-Hype rivers from the E-Hype Pinecast product. The boundary conditions come from this glossy 5 ocean reanalysis that Drew was explaining in detail about earlier, so I don't need to say too much more about that. And as I say, we assimilate sea surface temperature observations. For the operational system, we run with atmospheric forcings from our Met Office numerical weather prediction model. And one difference which we'd rather not have, but we do have at the moment, is we're using direct flux forcing. So turbulent flux is calculated by the atmospheric bulk formulae and passed directly to the ocean model. And actually within that statement, there are a number of differences, both that the bulk formulae themselves are different, but tied up in this, there are also some differences in the way penetrative radiation, for example, is dealt with. And so when we initially tried to switch to bulk formulae in our operational system, we found that model results were degraded, but we hope that we will make that change at some point fairly soon. We're using E-Hype rivers, but the operational product in real time. And Drew touched on this earlier, that our boundary data in this case comes from our Met Office 12th degree North Atlantic foam model. And these two aspects of atmospheric forcing and boundary conditions are two things we're looking at in the CMEMS context to look at running versions of this system with ECMWF forcing and also potentially 12th degree Mercator boundaries as well, just to see what the sensitivity is to those things and potentially switch in the future. Again, we're simulating sea surface temperature observations, and this is running with a daily initialization analysis and 5-day forecast, I suppose a 6-day forecast there. So that's mostly what I'm going to say about the forecast product. As I say, the rest of the talk will largely focus on the reanalysis. And the remainder of the slides really go through a number of different examples where you can see some benefit or otherwise, trying to kind of present a balanced picture of how downscaling performs in different aspects of the model. So this is so they're not all with up-to-date versions of the system, I should say. Some of these examples are pulled from earlier work. So this is an example when we were using the Polcoms model, which was a predecessor to the NEMO model and provided some products to MyOcean previously. And just looking at, this is a plot of the difference between surface temperature and the bottom temperature, and using some boundaries in this case from a very low resolution climate model, so I had CM3, so sort of 2 degrees of resolution, which as you see doesn't even resolve the channel, and the UK is pretty ill-defined in that case. And this is really just making the point, as I guess it's fairly obvious, but the downscale field doesn't just look like a sort of interpolated version of the original field with a bit more detail. The fact that you've got different processes, tidal mixing going on in this new downscale domain, and of course the differences in the bathymetry in the coastline make a really big difference in terms of the simulation that you get. This is coming slightly more up to date, so with newer versions of the system, and comparing in this case some salinity observations in the southern North Sea. These are from ferry boxes, so we've got quite a long time series of salinity observations, surface salinity, and comparing the observations in red with the Northwest Shelf reanalysis, this black line, and for context, the glossy reanalysis, which is the one providing the boundary conditions in this case, as I've talked about. And you'll see that the Northwest Shelf reanalysis is performing much, much better compared to the observations than the global reanalysis. And of course, there are always sort of a multitude of reasons why this is happening, because you kind of control experiments are never as clean as you might like. And a part of this is probably coming from the river flow. So global reanalysis will just use climatological rivers. This is using the E-Hype rivers in the Northwest Shelf reanalysis. And then along with that, you've got the additional resolution of the channel. Another example here, looking at the mean biases in near-surface salinity, so salinity over the top 5 meters in our reanalysis. And this is showing the benefit in this case of of the data assimilation in the reanalysis compared to the control run, which doesn't have any data assimilation. I think this is quite interesting because it's just demonstrating that although we're not assimilating any profiles, so we're not assimilating any salinity information at all, the assimilation of the SSTs is improving the model performance against profile observations for this salinity metric. So it's probably not particularly clear in this case, but you can see some of these darker red colours are a bit lighter on this side, and similarly with some of the bluey colours are a bit greener. So the SST assimilation is helping to correct the stratifications to some degree, and therefore improving the salinity in the model. Moving on to tides, which is again, I say, is one thing which generally speaking we haven't had in global models, and so we need some kind of downscaled higher resolution S-level model to do a good job of these. And this is evaluating the M2 component in this case, and you'll see that generally speaking you've got quite pretty good model observation correlation. Amplitudes, most of these circles are white, which indicates very small amplitude errors, except in a few places around the coast. Phase errors, generally reasonably good. As many of you know, the Northwest Shelf is quite a hard job to get the tides exactly right. It can be very sensitive to bathymetry, other aspects of the model, whether that's bottom friction or even version of Nemo that might have slightly different reference densities, things like that, which can have quite a big impact on your tide. So you do need a certain amount of tuning. Because of the locations of the amphidronic points, you can quite easily get larger phase errors than you might want. But generally speaking, this kind of performance is reasonable, and newer versions of the model, I think, are slightly better. We've been trying to look at some sections in the Northwest Shelf. These are sections which were agreed as standard sections a number of years ago within the NOOS community. And because the Now Maps consortium providing these CMEMS products has got a number of different members, they have access to various different observations that we're hoping to be able to make use of more over the coming years to validate the reanalysis against those observations. So to date, these are the sections that have been looked at. So you've got the reanalysis value here, and then in brackets the observational value against these section observations. And the model seems to be performing quite well. I've not shown on here the free run, but these are certainly better than for the free run. So the data assimilation is helping in that regard. Moving on to biogeochemistry, so one of the other components that isn't typically in a lot of global models, although of course there are exceptions. These are again results from some slightly earlier versions of the system. So there are some results on here from an early, so the blue line is an earlier operational system, the black line is a more recent Nemo-based observational system, comparing with some biogeochemical observations at a buoy near Plymouth, the L4 buoy. And you can see that although in general we would probably say that biochemical modelling is a less mature field than the physical modelling, we are now starting to do quite a good job. These the red in situ buoy data and the black line match up pretty well for most of these variables that we were looking at. And the changes here probably aren't to do with the specific model itself as such. They're probably more to do with exactly where the domain boundary was and the boundary conditions, where the boundary conditions were coming from, the quality of the boundary conditions. But one change between the earlier system and the more recent one was an improvement in vertical resolution, which we did find to have a significant benefit for these biogeochemical variables. And then this is perhaps a bit of a more mixed picture of some of the plots which are shown in more detail in the quality information documents for this product. And so I'd encourage you to have a look at that if you're interested. So the quality information there goes into more detail, obviously, in many of these things, and we'll increasingly be adding to that, providing more different metrics and trying to improve the information that we provide. And I think one thing to point out is that there are aspects where the model isn't looking particularly good. The control model without assimilation and the assimilative model here for a salinity profile, the same L4 buoy that I was talking about previously, you can see that in both cases they're far too mixed, and so you've basically just got uniform salinity over that profile compared to the observations, which obviously have more variability. So neither the free run or the assimilative run are doing particularly well. And I guess we want to make sure that the QUID provides the information that users want, not to just assume that a downscale product will be better. But if we're highlighting places where we know we wouldn't want people to trust that information, then that's really useful. We're not just trying to make our models look as good as possible. And then this is an example of some work by John Tinker looking at predictability. So finding some significant lagged correlations for some regions in the Northwest Shelf, both for sea surface temperature and salinity, looking at correlations with the winter NAO. And I guess in many ways they're not unexpected, but you see relatively high correlations in the southern North Sea at lags of kind of 1 and 2 months, particularly for SST and to some extent for salinity as well. And with predictability of the NAO, and Drew was talking quite a bit about that earlier, that does give some potentially useful predictability in this system. And then I'm going to go on in the last 2 or 3 slides just to mention a few of the developments that are being worked on at the moment. Some of these are relatively mature and will be happening next year. Some of them are slightly longer in the future. And I guess initially they're focused to some extent more on the operational forecast system, so looking at impacts in forecast case studies, that kind of thing. But with the intention that they would also feed into the reanalysis system as well. So one thing that's being actively worked on is increased resolution. I mentioned that 7 kilometres isn't particularly high resolution now for this kind of model. So we're looking at moving to 1.5 kilometre model. I'll show you a couple of plots from that system in a moment. We're looking quite intensively at coupling, both with wave model and atmospheric, and tied into that land surface hydrological models within a kind of unified Met Office environmental prediction system. And there's work being done at the Met Office by Hugh Lewis, part of which is funded by the CMEMS R&D projects. We're looking, and this is very imminent, at simulation of more data types, so TNS profiles and sea surface height, so that's something that will be happening from the next version, so CMEMS V3 early next year for both the forecast and analysis. The NowMaps consortium, sorry, just skipping to this one a minute. The NowMaps consortium has an intention to look at multi-model reanalyses, so there are members providing separate analyses with giving us scope to do that. We'd like to look more at ensemble forecast and sensitivity to initial conditions to provide uncertainty. And of course, a key one is this evaluation, working out what observations we can be using, what metrics we can be using, as Marie just touched on, trying to improve the way we benefit, show the benefit of these downscale systems compared to high global systems, and the benefit of the data assimilation, for example. So I said I'd come back to this image of the 1.5 kilometre resolution model. So this is the one that's being worked on, known as AMM15 within the Met Office. So it's obviously much higher resolution than the current AMM7 model, using a higher resolution bathymetry and so much more detailed coastline. It is a slightly different domain, so slightly smaller and a slightly different projection, but broadly speaking, it's comparable to the previous domain. And this is a nice image showing the difference between the sort of features that we're resolving in these two systems. So you can see much more of the sub-mesoscale activity here, and we saw figures similar to this in some of the sessions earlier in the week. So the marked contrast between the shelf area and the deeper ocean area in terms of the sub-mesoscale. So that's looking very promising. And we are seeing, this figure isn't particularly clear, but we are starting to see some of the places where we had biases in the, it might be a movie. If it is, I didn't realise that. And it probably won't play. No. No, probably not. I don't know. I didn't realise it was a movie. But some differences between the higher resolution model and the lower resolution model. We're starting to see evidence of a bit of cooling in the SSTs at the shelf break, where you've got a bit more mixing going on. We didn't see that kind of effect in our lower resolution model, where we found the SSTs were generally a bit warm on the shelf break. And also some differences in the SSTs in the northern parts of the domain that seem to be improved, perhaps due to the way that some of the currents are resolved in the northern part of the system. So generally promising, although that work's still some time away from becoming the operational system. So I will leave it there. And if you have any questions, I will attempt to answer them, but I may well not know.